Welcome back, Chemistry 30. This is the first video in the Chemical Bonding and Materials Science MS1 section, examining the role of valence electrons in the formation of chemical bonds. And with it, we'll look at the first section, Lewis symbols and the Octet Rule. Before I look at that, though, kind of an introduction here, basic concepts of chemical bonding. So you have this on your handout booklet. So we'll just highlight a couple of things here. So whenever two atoms or ions are strongly held together, we say that there is a chemical bond between them. And there are three general types of chemical bonds: ionic, covalent, and metallic. And we'll look at all three eventually. You can get a glimpse of these three types of bonds by thinking about the simple act of using a stainless steel spoon to add sugar to a glass of water. Table salt, of course, is sodium chloride, NaCl, which consists of Na plus and Cl minus ions close together. The structure is held together by what we refer to as an ionic bond, which we've taken in earlier courses, and that is due to the attraction between oppositely charged ions. So that's an important piece to highlight there. The water consists of H2O. The hydrogen atoms are bonded to one another by covalent bonds, and those are bonds in which molecules are formed by the sharing of electrons between them. So ionic bonds, we have atoms become ions, oppositely charged ions attract each other, that's how they're held together. Covalent bonds, though, held together by sharing electrons. You may have touched on that back in Science 10. Metallic bonds, so the spoon would be made up of iron. Metallic bonds are formed by electrons that are relatively free to move throughout the metal. So these three different substances, NaCl, H2O, and Fe, behave as they do because of the ways in which their constituent atoms are connected to one another, and in terms of what's happening with electrons too. What determines the type of bonding in any substance? How do the characteristics of these bonds give rise to different physical and chemical properties? The keys to answering the first question are found in the electronic structure of the atoms involved. That was discussed earlier, but hey, we're going to look at it here. In this chapter, we'll examine the relationship between the electronic structure of atoms and the ionic and covalent chemical bonds they form. And then metallics will be discussed later on. All right, so that's kind of an introduction. If you take a look at this page here, kind of going off what we saw in the previous one, metallic substances, electrons are delocalized, meaning that electrons are kind of move around in an electron sea, as it sometimes is referred to as. So electrons moving together, and that kind of helps hold the nuclei together. Ionic, we have something that's positively charged, something that's negatively charged, and are held together by positive-negative attraction. And lastly, covalent, we have electrons being shared. So the question up here is, what type of bonding would you expect to see in CO2, gas, carbon dioxide? Is it metallic, ionic, or covalent? So of course, C and O are both from the right-hand side of the periodic table. So of course, that's covalent bonding. Bonding between nonmetals that results in a covalent bond. Okay, Lewis symbols on the Octet Rule. The electrons involved in chemical bonding are called valence electrons, which for the most part are those in the outermost occupied shell. The American chemist G.N. Lewis suggested a simple way of showing the valence electrons in an atom and tracking them during bond formation using what we now know as either Lewis electron dot symbols or simply Lewis symbols. The Lewis symbol for an element consists of the element's chemical symbol plus a dot for each valence or outer electron it has. Sulfur, for example, has the electron configuration Ne3s23p4. Now, you may or may not have taken electron configurations. We're not going to dwell on it in this section. There are other ways we can take a look at valence electrons by looking at the periodic table, but they allude to electron configurations here. So just bear in mind that's what happens. But if we look here, those of you that did take it, we're looking at valence electrons are the outermost s and p electrons that are in the outermost orbital. So level 3, s and p, 2 plus 4. There are a total of 6 valence electrons. So you can see around the s there are 6 dots, each representing an electron. Now the easy way to do that is simply look at which group number sulfur is in. It's in group 6a, and look at that. Group 6, 6 electrons. So the group number for the representative groups that are A, 1A through 8, A, just simply look at the group number, and that's equivalent to the number of valence electrons it has. So relatively easy. The dots are placed on 4 sides of the symbol, top, bottom, left, and right, and each side can accommodate up to 2 electrons. So you see here on the bottom there's a maximum of 2, top maximum of 2, and then there's 1 on 1. All 4 sides are equivalent, which means that the choice of on which side to place 2 electrons rather than 1 electron is arbitrary. And generally, we try to spread out the dots as much as possible. So when filling this, we may put 1 on the top, 1 on the bottom, 1 on the left, 1 on the right, then on the top, then on the bottom. So try to spread them out as you're placing them on. In the Lewis symbol for S, for instance, we prefer the dot arrangement shown rather than the arrangement having 2 electrons on all 3 sides and none on the 4th. So again, spread out initially the first 4, and then start doubling up if you have 5, 6, 7, 8. The electron configurations and Lewis symbols for the main group elements of periods 2 and 3 are shown in the table below. Notice the number of valence electrons in any representative element. So those are the group A's, groups 1, groups 2, and then groups 3 through 8 is the same as the element group number. For example, as I mentioned earlier, sulfur is in the group 6A, so it has 6 dots. And so if you look down at this table here, group 1A, so the lithium element, now they have electron configurations here, but we don't have to worry about that. Just simply look at the group number. So lithium, 1 dot. Sodium, 1 dot, because it's all in group 1A. Some group 2A elements, beryllium, so 2 dots. Magnesium is also group 2, 2 dots, etc., all the way down to here. 7A, fluorine is in group 7, so it has 7 electrons. Chlorine is also in group 7, so it has 7 electrons. And then lastly, noble gases, group 8, so it has a full outer level, so therefore 8 electrons. And of course, helium is the only noble gas that has a full level of 2 electrons in its outer level. Okay, so relatively easy there. So if we look at this example, the area where it says give it some thought, are all these Lewis symbols for chlorine correct? So could it be this, could it be this, could it be this? So first of all, if we count, there's 2 plus 2 plus 2 plus, so there's 7 electrons around chlorine. So hey, it looks good, because if we look at the periodic table, chlorine is in group 7A. Over here we have 2, 4, 6, and 1 electron here, so yeah, that looks good. But lastly, 2, 3, 4, 5, there's 5 electrons, so nope, that's definitely not right. Okay, easy stuff. The octet rule. Octo is the prefix for 8, so of course 8 electrons are the maximum we can have. Atoms often gain, lose, or share electrons to achieve the same number of electrons as the noble gas closest to them on the periodic table. So quite often if we look at the left-hand side of the periodic table, it's the noble gas that's closest to them is on the right-hand side, and they get to there by losing electrons, whereas nonmetals, the noble gas is closer to them if they gain a couple of electrons. The noble gases have very stable electron arrangements as evidenced by their high ionization energies and low affinity for additional electrons or lack of chemical reactivity. If you take a look at what that means, maybe just over here on the side we'll get this down. If you've never encountered this before, ionization energy, energy to ionize, energy to make an ion, energy required to remove an electron. And electron affinity, the word affinity means that you want it, you want to attract it. So likelihood of an atom gaining an electron. So if we take a look here, where are we at here? The noble gas is very stable electronally because high ionization energy. It's very difficult to remove an electron from a noble gas, and also it has a low affinity, means it doesn't really want any extra electrons, and that's because the noble gases are stable. So they have 8 electrons, so they're not going to want to gain anymore, they're not going to want to lose any, so they simply stay like that. Alright, I think we'll stop there and we'll come back with part 2 of the video in a moment.